Okay, so right now we're going to cover section 9.5, which is about absolute value, piecewise, and greatest integer functions. I'm going to go ahead and point it out right now that most students tend to have a problem with piecewise functions. We're going to do two examples, but if you get stuck or have any questions, please do not hesitate to reach out to me. The first type of function we're going to talk about is an absolute value function. Remember, when I take the absolute value of a number, it measures distance from the origin of the number line. So let's look at this x-axis like it's our number line, because it is a number line. We remember that the absolute value of -6 is 6, right? That's because it's 6 away from the origin. 1, 2, 3, 4, 5, 6. The absolute value of +6 is 6 as well, because it's also 6 from the origin. 1, 2, 3, 4, 5, 6. So what the absolute value function does is it takes every value of x and matches it with an absolute value. So -2 goes to +2, -1 goes to 1, 0 goes to 0, 1 goes to 1, and 2 goes to 2, right? This looks a little funny because it has this severe right turn, right? But it is still a function because it does pass the vertical line test. So think of it as kind of a more angular parabola. Keeping that in mind, why don't we take a look at some graphs of absolute value functions and how those change over time. So the first one we're going to graph is this one right here. F of x equals the absolute value of x plus 2. Okay, so let's go ahead and make ourselves a little table of some values we could take an absolute value of. Before, when we were working with parabolas, +2, adding a 2 out here, resulted in a vertical shift. So let's keep the absolute value of -2, -1, 0, 1, and 2. So if I take the absolute value of -2, that's going to be a +2, plus 2, that gives me a y value of 4. If I plug in -1, the absolute value of -1 is 1, plus 2 is going to give me 3. The absolute value of 0 plus 2 is 2. And we find that we have some symmetry here, right? Absolute value functions are symmetrical across the y-axis. So let's go ahead and plot this. I have when x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. And that's going to give us our absolute value function. So just like parabolas, when I add a constant outside of our grouping symbol, that results in a vertical shift. We already graphed this one. So let's take a look at I have f of x equals x plus 2. So now I've added a constant within my grouping symbol. Before, that meant we were going to have a horizontal shift. And that's true. But we're going to have a horizontal shift in a different direction than we think. So let's go ahead and take a look at -1, 0, 1, and 2. Oh, and -2. Okay. So if I have f of x equals x plus 2, -2 plus 2 gives me 0, so my y value is going to be 0. If I have -1, -1 plus 2 is going to give me an absolute value of 1. If I have 0, I'm going to have 0 plus 2 gives me an absolute value of 2. So why don't we go ahead and plot those points and think about whether these were really the best 2 points to pick. So I'm adding a constant, but I'm shifted to the left 2. So I'm adding a constant of +2, but I shift to the left. So when x is -2, y is 0. When x is -1, y is 1. And when x is 0, y is 2, right? This looks like half of our absolute value functions. We can already kind of predict that the absolute value of 1 is going to be 3 and 2 is going to be 4. So let's take a look at some more negative numbers. What if I have when x is -4 and -3? So if x is -4, -4 plus 2 is going to give me a -2. Absolute value of that is 2. If I plug in a -3, -3 plus 2 is going to give me -1, which will give me a +1. So remember, when we are adding inside our parentheses, if we add a positive number, it's going to shift it to the left. If it was minus 2, it would have shifted to the right. So let's bring both these graphing techniques together. So I have x minus 3 plus 1. So that means I'm going to have a horizontal shift of positive 3 and a vertical shift of positive 1. So I can already tell from my original quadratic equation what it would have been. I'm going to be moving up 3, to the right 3, and up 1. So I suspect this is going to be my new vertex. Let's go ahead and figure out some values to see if my hypothesis is right. So I'm going to look at when x is 0, 1, maybe just 1, 2, 3, 4, and 5. So when x is 1, 1 minus 3 gives me a negative 2. The absolute value of negative 2 is 2. 2 plus 1 is 3. When x is 2, 2 minus negative 3 gives me negative 1. The absolute value of negative 1 is 1. Plus 1 gives me 2. If my x value is 3, 3 minus 3 gives me 0. Well, the absolute value of 0 is 0. Plus 1 is 1. And I know I'm going to have some symmetry here. So this would be our new graph. So I have when x is 1, y is 3. When x is 2, y is 2. When x is 4, y is 2. And when x is 5, y is 3. Here's my beautiful new absolute value function. And we can see that we had our horizontal shift and our vertical shift, just like before when we were graphing parabolas. The next type of function I want to talk about is a piecewise function. So it's called a piecewise function because it's defined for different rules over different intervals of the domain. What does that even mean? It means we're breaking up our x-axis into chunks. So for this red chunk over here, our function is defined by a line. For this blue chunk here, our function is defined by the horizontal line y equals 4. And then for this section of our domain over here, we're defined by a parabola, okay? So it's going to tell you how to break up your interval when it gives you the instructions for the piecewise function. Let's go ahead and graph one. So here I have the line 1/2 x plus 2 if x is greater than or equal to negative 2. So where's negative 2? Right here. So I care about when x is greater than or equal to negative 2. This kind of divides my domain into two halves, right? So in this half, when x is greater than or equal to negative 2, I have defined by the function 1/2 x plus 2, keeping a note that negative 2, because it's greater than or equal to, is included on this half. And then on this side of my graph, I have negative x minus 3. And that's when x is less than negative 2. So the boundary is not part of this side. I know how to graph a line, so let's do it. So I have 1/2 x plus 2. Positive 2 gives me my y-intercept. My slope is 1/2, so I go up 1 over 2. Up 1 over 2. I'm going to go ahead and graph my line. I'm going to put a solid dot on our boundary, right, because our boundary is included for this function. So here we have our line. Awesome. Now why don't I go ahead and switch colors? I haven't gotten that fancy yet. Let's go ahead and switch colors. How about blue? So now I have, on this half, negative x minus 3 is my function. Okay, negative 3 is my y-intercept. It should be over here, right? And then my slope is negative 1, so I know it's going to look like it's going downhill. So I know I would be going downhill. And we can kind of imagine that our line would be over here. So I've got a circle here, right? Because this would be part of the line if I could actually draw the line. And I've got a slope of negative x. So here is the graph of our piecewise linear function. This one was really nice. It broke my domain up into 2 chunks, okay? The next one is going to break our domain up into 3. So let's take a look at this. When x is less than 0, I have x squared. Okay, so on this interval, from when x is less than 0, here's where x is 0, over this section I have the function x squared. Now I have when x is between 0 and 3, my function is 2. So between 0 and 3, 1, 2, 3, here's my second section. I just have that f of x is 2. And last but not least, when x is greater than 3, I have 4 minus x. I'm going to write that as negative x plus 4, right? That'd be easier for us to graph. So why don't we go ahead and graph x squared? I know my parabola. When x is 0, y is 0. I'm going to put an open dot right there because 0 is not included in this function, right? It's included over here where there's a less than or equal to. When x is negative 1 squared is 1. When x is negative 2 squared is 4. Here's the graph of my half a parabola. Okay, so next, let's try magenta. So now I have that my function is 2, right? F of x equals 2. So when x is 0, y is 2. When x is 1, y is 2, right? This graph is going to be a horizontal line, and my endpoints are included. I'm trying to make those circles nice and big because I have 0 is less than or equal to x, and x is less than or equal to 3. Next, I have negative x plus 4. That's a line. It's going to have a negative slope. My y-intercept is 4, right? It's supposed to be over here. Let's go ahead and but plan out what our graph would look like. So here's where my y-intercept would be. I've got a negative slope, negative slope, negative slope. Okay, here's the first point. It's going to be open because remember it's when x is greater than 3. There's no equal sign. And I've got a slope of negative 1. Down 1 over 1. Down 1 over 1. So here is the graph of my piecewise function. What I would always start with when you're approaching a piecewise function is figure out how your domain is split up. That's going to be this column right here. Go ahead and make your nice little dashed lines and then graph each function individually, section by section. The last type of function I'm going to talk about is the greatest integer function. The greatest integer function is denoted kind of like double brackets, and it assigns the greatest integer less than or equal to any real number in its domain. What does that mean? So we can see that anything less than 1 rounds down, right? It graphs to 0. Anything less than 2 rounds down, graphs to 1. So 5 would go to 5. Negative 2 would go to negative 2. 0 goes to 0. But 6.5, we would round that down and go to 6. 3, we would round that down and we'd go to 3. Negative 1.7, that has to round to the next lowest negative number. That's going to be negative 2. And negative 1.5 would round to negative 1. So that's a quick look at the greatest integer function. Now we've covered all of Chapter 9. Next we'll be starting Chapter 10, and I look forward to making those videos for you guys next week.